Hi, I'm Rachel Myers. This is the first time that I've walked out to a smoke machine before. This is very exciting for me. So, there it is. Okay, cool. So, I'm going to give what I hope will be a somewhat controversial talk today. Services considered harmful. Before I start, I have to say something about all the pictures. These are all amazing drawings, and I didn't draw any of them. They're from an online cartoon called explodingdog.com. They're hilarious and sad. Sometimes they're very poignant. They're drawn by a guy named Sam Brown. And I modified them all. I drew skirts on all of them using the Keynote drawing tool because now they look more like me. And I also drew some architecture diagrams, and Sam Brown didn't draw those. So to recap, this is amazing. This is better. Okay. So I have a day job. I work on the new user experience team at GitHub. So those are the people that are trying to make it easier for people who are new to coding or just new to Git and GitHub to join the community and get started. Aside from that, I'm on the board and a volunteer at an organization called RailsBridge. And RailsBridge holds free workshops around the world to teach women and other marginalized groups Ruby and Rails. So if you want a RailsBridge near you, you should talk to me and I can help. I also volunteer with Foundry. That's an organization that works behind the scenes to make RailsBridge, Enclosure Bridge, and Mobile Bridge all possible. So if you have a technology that you want to get into the hands of marginalized groups, I can help you with that too. Okay, all of that stuff out of the way, let's talk about services. Most people are probably familiar with service-oriented architecture, but just in case, and to make sure everyone's on the same starting place, SOA, service-oriented architecture, is a style of software architecture where we're going to build and deploy distinct services in place of a single monolithic Rails app, or just app. The goals of building SOA vary, but to generalize, the hope is that it's easier to maintain and scale those small services than a large monolithic application. So there are a lot of promises that are made about SOA, and they're not really presented as a trade-off. It's been presented by some as the cure for the modern web app. I'm going to say this slightly mockingly, but I think you can find references for all the things I'm about to say. Is your app slow? You should build services. Is your app complicated and not well understood? You should build services. Is your database falling over under load? You should build services. Do you have organizational problems? You should build services. In practice, the benefits of services are more nuanced than that, and I think there's some clear trade-offs involved in moving towards a service-oriented architecture. So there are lots of books and blog posts and talks that focus on how to build out services. And I would like to see more content that focuses on the ultimate success or failure of breaking these large apps into smaller services. So this is an attempt to start that conversation by examining honestly what I've seen and sometimes what I've caused to go wrong. I don't know if it shows up. This is a little dog sitting in a closet. He's saying, sometimes I sit in my closet and I think of all the terrible things I've done. That's the origin of this talk. I'm going to walk through 3 cases that I consider instructive about what services haven't really provided. And then I'm going to give one case of what I think services can do well. I'm going to conclude that services can be a great solution in specific cases, but we shouldn't be trying to replace all of our large Rails apps with services. And to clarify, these stories are not from GitHub. The customer-facing experience of GitHub.com is a large monolithic application, just one of them. And that's because the trade-offs of building services have not, to this point, been worth the potential benefits for us. So all these stories are true, but I have changed the domain model in all of the code snippets to be a company that specializes in selling hats to dogs. I've called it Hats for Dogs. You guys don't laugh. Fine. So to set the scene, I'm working on this web app, hatsfordogs.com, and the code has become a hot mess. For years, we've focused on quick iterations at the expense of refactoring and paying down our tech debt. And now we've realized that we're sputtering. We're moving more and more slowly, and there are some models that are very important to our app, and we're entirely afraid to change anything there. So we've gotten some buy-in from management to spend time turning this situation around. We're not going to entirely stop development, but we're going to prioritize code quality as we continue to build things out. This brings me to my first case study for services. The team gets a feature request for a long-neglected part of the website. This is a little part of the app that had become more tangled than others. And here's what it does. So there are a bunch of products that we might sell on the website, and you get to vote. I like this product. I don't like this product. And then the winning products are ones that we will sell on the website. So we want to add a small feature to this. We want to add a small feature enhancement to this feature. And we see this as an opportunity to extract this tangled mess of code that we have. So the client-side code for this feature continually interspersed behavior, presentation code, and obscure browser fixes. In some cases, we didn't even know if those fixes for those browsers were still for browsers that we supported. Amazing. And it had reached the point that the team considered the JavaScript unrefactorable, which is an amazing concept. And the feature for this code, the feature that this code is supporting is a simple voting app. It didn't need to be complex. The code is dauntingly complex because it has no structure, and there are no comments that even hit at what some of this stuff is about. The server-side code for this feature has an entirely different problem. The hats that you could vote on, which are not yet products on the website that you could buy, were the same class as hats that you could actually buy on the website, even though the behavior of these two objects is entirely different. To make that more confusing, if a hat ends up as a winner, we create a second record, same class, and we create an association between those two objects. It's kind of amazing. So this is a pretty confusing data model to start off with. And if we had been managing our complexity well, if we had been following, for example, the advice of Sandy Metz, we would have seen that this class was violating the single responsibility principle. We could refactor this into two different classes so that each class is defining one set of behavior. But we thought that building services was an alternative approach to managing complexity. It's not. And we thought that we'd be able to refactor as we wrote those services. So we didn't bother to refactor the model in place. As we set out to build this service, the problem that we wanted to solve was that we wanted to refactor this kind of mangled code to follow the single responsibility principle. And specifically, we wanted to separate what I'll call buyable hats and votable hats. Secondly, the front-end code was so confusing that we considered it impossible to refactor. And we thought we could see some clear lines about what we could change there. In other words, both the client-side code and the server-side code had unmanaged complexity. There's a lot going on, and it was difficult for developers to understand it. So I'm going to step away from my services story and just make some general points. When it comes to practical advice on managing code complexity, the best advice that I know of comes from Sandy Metz in her book, Practical Object-Oriented Design in Ruby. It focuses specifically on reducing or managing complexity in your applications. The book is full of tons of great ideas, and I'm just going to pull out a few that I consider the most relevant right here. First, most relevant to this story, we should make each class and method conceptually simple. So that doesn't mean that you can't have internal complexity there, because we all work on apps that have a lot going on, and so you have to have some place to put the complexity. But each class can describe just one thing, and each method can do just one thing. So that usually means in practice that methods are going to become shorter, readable, well-named. As a side effect, they also become easy to change and reuse. So in this, in this class, we have new and old products. This is a very made-up example. And they're describing two different types of behavior. We're going to even initialize them differently. So we could just refactor that. That's an easy example. Unfortunately, those sorts of refactors are a ton of effort, usually, and then you don't, at the end, have a new feature to show for all that work. So it's sometimes necessary to compromise. We could concentrate our efforts on reducing the complexity in the most important code paths, the ones which change often. And tightly coupled code in those parts of the applications are the ones that are most likely to slow or halt development. So it will prevent us from changing or extending our application. And that implies a third point that I just want to make explicit. It's not usually worth the time and effort to refactor away all complexity. That will go on forever, and you'll never build anything new. So extremely stable code paths or code at the end of the line in computation, that doesn't really get in your way, and you don't need to change it often. So you won't get a lot of bang for your buck if you spend time refactoring it. So those are three principles that we could have used to rewrite and refactor this feature. We could have refactored that hat model into two classes, or if you're into inheritance, you could have a base class and subclasses. And the important point here is that we could have done it in place, and that would have helped us understand what we were dealing with better. But we had to fly our own way. We thought that we could refactor as we went, so we didn't bother to do that. So we went to make a small feature improvement, and we thought as we would do that, we would also refactor everything. We're trying to do too much at once here. Specifically, in separating buyable hats and votable hats, we went, let's see. I lost my place in my notes, it's fine. Oh, OK. So we started off, we ran Rails new, and we defined the data model that we had always wanted for this feature. It was really fast at first. It was glorious and fast-moving because we knew the existing feature well enough that we didn't have to struggle understanding new business requirements. And we had enough experience with the existing problems that we knew there were some very set patterns that we wanted to avoid. So we went fast for a while. And then we hit our first speed bump when we started planning how to import the old votable hats records, which were really hat records, into the new votable hats application. It was a doozy of a speed bump. The migration script that imported votable hats and some of its associations into our new application were the first place that we encountered leaky logic. So all of the logic around hats wasn't just in the hat model. It was spread out all over the place. So in order to recreate the customer-facing state of this hat, we needed things from here and there and there and there. And migrating all that data in a way that would not disturb the customer-facing experience meant a lot of small hits in our velocity while we spent time understanding parts of the application all over the place. Eventually, we realized that votable hats had more dependencies on buyable hats than we initially realized because we hadn't refactored the hat model enough to understand those dependencies. So here's what happened. We started off with our main application and our new votable hats application, and they each had a database associated with them. And we did one bad thing. We connected to our old database so that we could just get info about the existing hats. This should have been a warning sign for us. Then we realized that the main app also needed some attributes about votable hats, and we couldn't wait for the API to be built. So the main app connected to the votable hats database. And we should pause to appreciate that this is the diagram of doom. This diagram means that we didn't actually understand the code that we were extracting well enough to actually extract it. We drew the lines around our new service so poorly that we're not actually extracting anything. We're creating an ecosystem of services that mirrors our poorly factored code of our original app. And it got better. Realizing that there was so much complexity in the hat model and its associations, and fearing the time that it would take to understand and refactor away that complexity, we packaged the hat model and associated models as a gem, and we included that gem in our new service. This is a failure. This is a huge failure. So what went wrong here? Classes, we need to create classes with well-defined responsibilities and boundaries. We should have done that before we ever tried to extract anything into a service. In other words, refactoring away your complexity is a precondition to building services. Services are not an alternative solution to managing your complexity. Secondly, the teams that were attracted to rewriting the gnarled code into services were doing so as a way to avoid understanding the existing app. That is entirely the wrong motivation to undertake this sort of project. So if you have unmanaged complexity, refactor that into something that you can get a handle on, and that's the only way to know if you can really extract it. So when I think back onto this app that I worked on and the mistakes that we made there, I can't help but think about how this problem would be approached at GitHub. GitHub.com is a giant monolithic app, and there are corners of it, inevitably, that are neglected, poorly understood, and poorly tested. And this makes refactoring risky, but also absolutely essential. So to help with refactors and rewrites like that, GitHub maintains an open source project called Scientist. Scientist lets you define an old and a new code path, and then in production, Scientist runs both of those code paths and reports back when they agree or disagree. So users will see the result of the old code path until you flip the switch. So it's a way to dark ship your code and test your rewrite with actual users in real production data. Jessie Toth gave a talk called Easy Rewrites with Ruby and Science about how she used Scientist to rewrite the permissions code of GitHub, and it's a great example. In her case, that code was not fully understood by anyone in the organization. It was often poorly tested. In other words, it was the worst possible code to rewrite. She investigated all the corner cases that were coming back from scientists when the code paths disagreed. And when the permissions code finally shipped, it was tested, reliable, and well-factored. So it was a really impressive rewrite. And it was even more impressive because it's almost impossible to do well. So, second case study. Around the time that the Votable Hats app was failing, we were contemplating other services. And we thought that a service that would manage our authentication and authorization for all the applications we were going to build would be an important step. So this is the story of building an identity service, or as I call it, how I learned about queuing theory. We set out with a few problems to solve. First, it was enticing to build an identity service because the complexity of our monolithic app was concentrated in our hat model, what some would call our God model, and our user model. So we hoped that pulling the identity service into a separate app would help us isolate the complexity of the user model. We were also beginning to have problems with team ownership that some of you might find rings true for you. First, the teams that consumed the API of the main application, and so therefore had API feature requests, would merge their own changes to the API for themselves without consulting the team responsible for the user API. They needed something, so they did it. Secondly, we were seeing more and more of what we termed swoop and poops. It's like what a seagull does. Someone flies in, criticizes code that they are neither familiar with nor responsible for, and then they fly out before they have to help create a better solution. It's really fun to do, and it's really bad to be on the receiving end of a swoop and poop. It was especially problematic for the team that was maintaining the user model. So extracting that code into a separate repository seemed like it would give us both the complexity management that we wanted and the organizational separation that we kind of needed. I make the same mistakes, but I can't stop. That's what I did. So we knew that we didn't want to end up with the closely coupled services like we had with the Votable Hats app, but we still saw services as the solution. So we didn't want to give the identity service a database of its own. This was our solution to not having tightly coupled code. When a request would come in, it would go through the main application, it would call the identity API, that would query the database of the main application, and then return a response the same way. So it was a little circuitous, but it wasn't terrible. Oh my God, something's happening with my slides. Actually, I can see that all of my images are disappearing. Ooh. Is there an AV person? OK, we'll just try this anyway. It'll be fine. So this is around the same time that we built an iOS app. There used to be another little square here that had an iOS app. The iOS app would need to authenticate users just like the main web application. OK, so this is really amazing. This shows the outline of my images, but not the actual images. This is like an amazing problem with Keynote that I've never seen before. So I can fill it in for you. It would be reasonable. So this little box down here is the iOS app, and then the one above it is the mini app, and this one over here is the main application, and then the database above it. So it would be reasonable, given that you're going to have a mobile application, to think that you could authenticate against the identity service, which would query the database, and return a response to the mobile app. But again, the user objects were modified in so many places across the main application that we were never able to fully extract all of the user behavior into the identity service. So now we get our images back. Cool. I have no idea what's going on with this computer. It's exciting. So as a result, the identity service needed to call back to the main application for every authentication and authorization call, including those from the mobile app. And this is terrible because you have to be authorized to do almost everything on the website. So this is a failure. We did extract the identity service, but it couldn't do anything on its own. And this is a much more dangerous failure than the previous example. First, it brought non-trivial operational complexity. We had to keep this up all the time. And more seriously, the identity service wasn't capable of functioning without the main app, and the main app wasn't capable of functioning without the identity service, meaning both applications need to be up all the time for the site to be usable. Instead of one single point of failure, we now had two. Worse still, the identity service didn't relieve the load of the main app in a meaningful way. It's common to hear service-oriented architecture touted as a way to reduce app load, and so doing to help scale applications. But SOA and scaling is actually more subtle than that. So this is how I learned about queuing theory, and it takes a little bit of explanation. To start out, we naively believed that anything that would reduce load on the main app would help the scalability and server response times. I can say that now, and it still kind of seems reasonable to me. For example, if we needed 1,000 workers for the main app, and we added 100 workers to handle just authentication, we thought this would be an improvement. Yay. However, ignoring all the extra time that we would require for all the extra network calls, which you can't really do in real life, but just to abstract that away. If we have a total of 1,000 workers serving requests for the main app, and only 100 workers for requests on the identity service, the identity service could create a bottleneck and slow down the user experience. If queuing theory is a little bit new, here's how I explain it. It's like the most inefficient coffee shop ever. So I have to stand in line to order my coffee, and when I get through that line, I have to go get in another line to pay for my coffee. And when I get through that line, I have to go get in another line to pick up my coffee. So with a monolith, I only stand in one line. So standing in all those lines is going to take extra time. And it's possible to make that multi-line coffee shop as fast as a coffee shop with just one line, but it requires that you scale up lots of different things. For example, I might have to hire a bunch of people that take orders, and that's all they do. And then I have to hire a bunch of people that only make coffee, and that's all they do. And that's what it's like to scale with services. Instead of scaling up workers that can handle any request, I need to scale each service independently. So in the case of the identity service, for the same amount of resources, we could have gotten a faster average response time if each request could be served by any available worker. And to be clear, this is because we're fetching user information on every single request. So that calculation would change for services that were used less frequently, or that could just time out without creating a devastating user experience. So the other goal of that project was to define clear team responsibilities by creating separate repositories. This is another case where I like an existing GitHub solution. So creating a separate repository for just the identity service did indeed prevent people from making changes on that repository. But they continued to make changes that would affect the user model. They just made it in the main application, which they had access to. So it didn't solve the core problem of teams not respecting areas of responsibility. And at GitHub, we have a really low-tech solution. We have a YAML file that defines team responsibilities by controller. This is just like a made-up example from it. This file is used on our issue tracker, so when exceptions occur in an area that I'm responsible for, I'm set up to see those immediately. And that means that I don't really want to create problems for someone else because I know that they'll be pinged if my code is buggy. So that also creates the expectation that if I open a PR, a pull request, on a part of the app that I'm not responsible for, someone in that area needs to sign, someone that's responsible for that area needs to sign off on that PR before I merge my changes. So that brings me to my third case study for SOA failures. And this is one that was not destined to be a failure, but the implementation made it one. When we had a monolith, we had one set of assets for the entire website. Then we had several customer-facing applications. We had a mobile web app, we had mobile native apps, and then we had multiple apps that were backing the normal web experience. So we wanted to find a way to share assets across all these applications rather than repeat them in every place. And if this sounds weird, these are things like the header, which is visible everywhere, the content for a login modal, which would sometimes be cute and would sometimes change, and we wanted it to change uniformly. There was also content that was unique to each application, but most of it wasn't. So like the size chart is another good example. So as we thought about how to design our shared assets, we had one main problem that we were thinking about. We wanted to avoid repeating this and avoid repeating our assets in every single app. Even if that was copying and pasting them into every single app, we didn't want to do that. So we came up with the idea of adding a gem server that could serve a gem that just contained all of our assets. And we had various user-facing applications that each needed them. So they could just when you bundle in each app, you could just fetch it from the gem server, and it would get the newest version of that gem. So we tried this. We bundled it all up. We included them in our app. It was a really cheap solution because it's easy to package a gem, it's easy to include it, and it's easy to reference those assets in your code. The problem came when the assets needed to change. It's kind of hard to see, but that's like a little tick mark, so the gem incremented. And when the assets change, those are sometimes dramatic customer-facing changes. So in those cases, we wanted the assets to change uniformly. Unfortunately, that's not how gems work. So think about the case of a site redesign. This really happened. In the case of a site redesign, we could increment our gem version, and then we need to coordinate updating the gem across all of the applications and then redeploying that change at the same time. So while we were doing this, it was fairly common to show an inconsistent experience while we tried to redeploy everything. And this is still an improvement. It drew the right boundaries in some ways, and because it essentially automated the copying and pasting of assets that we would have done by hand. But this implementation is also a failure. It became a pain point because we forgot an important business requirement, that assets will need to change uniformly. So it essentially became a problem of cache invalidation. We need to invalidate our cache for all these assets across all of our apps quickly. This solution would have been okay if the boundaries around the applications themselves had been drawn differently. For example, if the assets for a single experience were coming from the same place, this solution would have worked. This is an exaggerated example, but this is what happened because one user experience was coming from multiple apps. A user would be shopping on their laptop. They would go to a home page, they'd go to a category page, and when they tried to sign in to buy something, they would get an entirely different looking page. It's not the best. So it would have been more acceptable for the mobile app to be inconsistent with the desktop because I don't jump between those in the course of shopping. This, however, is really terrible. So I could go back and, if I could do it over again, I would add the requirement that we could have, in retrospect, improved our implementation, and that is that assets should change together. So if I want to re-architect this is not what we did. Everything that I'm saying now is made up. We didn't do this at all. So one solution that we could have tried instead of caching the assets in each application, because that's essentially what we were doing, would have been to create an asset service. The apps could request assets directly from that service rather than caching them. And this would give us other problems. We'd have to think really hard about what our CDN configuration should be, how long should those assets live. But we should be doing that anyway. We could have combined this strategy with drawing more careful boxes around our customer-facing apps. For example, we could have tried out a model where our front-end app is responsible for all the assets of an entire experience, and we could have separated that from our back-end, for example, pulling apart our API and our client. That's a really reasonable line to draw, I think. And just because I've been doing this for every example, at GitHub we don't have this problem. We have a few different packages that do share assets across applications, and we do run into pain points when we try to increment those, but crucially, that is not a customer-facing problem, because the customer-facing application is served from a single monolithic Rails app. Updating the assets in each app can move at its own pace because the most customers will ever see is a single app. So far, these are all stories of service-oriented architecture gone wrong. But I want to try to learn from my mistakes. So I want to kind of think about these and see, are there cases that I can kind of pull out from these and think about how SOA could be an advantage. So here are the things that I've learned. First, service-oriented architecture is not a mechanism for managing complexity. In fact, a successful SOA requires that you've already refactored your code to be something that you understand. So you have to manage your complexity, and then you can try to pull it out. Along similar lines, separate repositories do not magically create isolated code. That's an organizational problem. Secondly, the overhead of service-oriented architecture, like the additional network calls, the scaling problems, those might be justified depending on the needs of your apps. For example, if you need to run your code in multiple places, like the asset service, or if your app has dramatically different uptimes, those might be good cases that justify the overhead. So with that in mind, oh wait, I have one more. Lastly, it's possible to create services that don't interfere with the customer-facing experience. So if I went to build services again, I have to keep this in mind. The most important business requirement is to not bother your users. So that's like my primary thing that I want to take away from this from now on. Now I have one success story, because I tried to give this talk before. And all the questions that people asked me were, why would you ever even try to build services? So I thought I would include one case of where services worked out well. Going back to hatsfordogs.com, there was an example, one that did especially work out well. It was a service that allowed customers to take pictures of themselves wearing the products, and then we would include those pictures. So this is the, I'm in violation of the Sinatra copyright right now. This is the logo for Sinatra, because I'm lazy. So this is the product page in animation form. It includes a picture, a description, the price, and a buy button. This is everything that we considered essential for customers to buy things. Okay. So we let pictures, yeah, thanks. Well, that was even worse. That's okay. Thanks. So this feature would let people upload those pictures, tag the products they're wearing, and then we'll show those pictures underneath the product. As we set out to build this, we had a few design constraints. First, the gallery photos are not at all essential to buying things. They're just a bonus. So this feature has very different uptime requirements. If this gallery goes down or is ridiculously slow to respond, that's fine. We'll let it time out, and the site can stay up, and users can still buy things. So if we think about the queue that we're creating here, we're creating a queue, but it's a queue that happens after the page is shoppable. So crucially, this is going to AJAX in. If it wasn't AJAXing in, it would block the page. But we wanted to make sure that we didn't interfere with that time to interacting with the page, so we made sure that it would come in later. So we can enqueue as many things as we want after this point, and it's going to be OK. You probably shouldn't do that for everything, but in some cases it's fine. Secondly, we could have built this as part of our monolithic Rails app, but we wanted to make sure the photos didn't slow down the time that was. Okay, in the unlikely case that this had been an incredibly popular feature, maybe it could have brought down our Rails app, right? So we wanted to isolate the core functionality from any viral takeoff that we might have experienced. That was very optimistic, by the way. We didn't have that problem. So to make sure no workers are serving up code that could be being used to provide a fast core shopping experience, we wanted to isolate the core application from any additional load. And this worked out actually pretty well. There were some quirks. I won't say that it was perfect. And if you've ever tried to optimize your front-end performance, you know that you should try to avoid the things like we did, where we're AJAXing in content that requires the page to repaint after load. But we made that compromise by repainting the page below the fold. So most users didn't even notice it unless they were very interested in this product and actually scrolled down. Speaking of performance, I've used the word performance a little bit inconsistently today, so I just want to clear this up. When I say that the photo gallery could have affected performance of the core shopping experience, that's about server performance. It's about how many workers are available to serve requests and how long those requests take. And when I think about how our architecture affects performance, there I'm thinking about how long until a user can use the application. So that's an entirely different type of performance. And there are a ton of websites that take server performance really seriously. They've made sure they have no N+1 queries, and they select only the attributes they need for each query. They log their slow queries and then investigate and fix them. But sometimes those same sites don't bother to turn on gzip or manage their assets carefully, turn on, start using sprites for their images or shard their asset host. And those are the things that are going to impact the time until a user, the time that a user has to wait while your page loads. So this front-end focused definition of performance is the one that I mean when I say the photo gallery shouldn't block core functionality. The page needs to be shoppable, and that's my first job. So just to keep in the back of your mind that improving the time to a user improving the time that user has to wait to interact with your page, this is the single most important thing that engineers can do to improve user engagement and conversion rates and conversion values, assuming that your company has a business model, which they don't all have. It's fine. It's time. OK, so I have one more slide, and it is a giant monolithic robot that everyone is taking care of. And this is what we should be doing. We should be taking care of our giant monolithic Rails apps. And if you disagree with me, I love to argue. This is me. Thanks.